Hello everyone and welcome to PC Retro Tech. In this week's video I'm going to be looking at a VGA graphics mode called Mode X, which is used in a lot of games but isn't an officially supported VGA graphics mode from when IBM introduced the VGA adapter in 1987. Instead, it was subsequently developed by programmers trying to get the most out of their VGA hardware for their games and demos. Now, given the enormous amount of interest that was generated on the channel by the most recent video on this machine, the IBM Model 30, there's a link above if you want to see that video, I was going to call this video, Can the Model 30 do Mode X? But it turns out there's a very simple answer to that question, no it can't. You remember that this machine has a kind of proto-VGA adapter in it called MCGA, which was introduced a little earlier in the same year that IBM brought out True VGA, but it only had one of the main new VGA graphics modes, the so-called Mode 19, or MCGA mode. Now, when I made the video on the Model 30, there was a lot of information that's come to light that I wasn't aware of. Even some of that has surfaced on YouTube very recently. And so I want to go into that information because it'll give us a little bit more of an insight into the difference between MCGA and VGA, how this machine works, and about the subsequent development of VGA and of course Mode X itself. We're inside the Model 30 now, and we're able to say a little bit more now about what the various chips in the video circuitry do. And that's thanks to a video by Hakemon Mike, which I have a link to in the description. Some viewers pointed this out. He also has a link to the schematics for the Model 25, which is very similar. It has MCGA as well. Now, we'd already identified that this chip was the RAM DAC, or as IBM liked to call it back then, the color lookup table. And this is the one that has the 256 color registers in it, which determine the colors that are visible. You can only have 256 colors at a time in MCGA. And so each of those registers is 18 bits. There's 6 bits for red, green, and blue, and that gives you a total of 18 bits each. So you have many colors to choose from, but you can only have 256 at once. Now you have to be a little bit careful about calling this palette registers because although that may be fair terminology for MCGA, when you get to VGA, palette registers refer to something else, and so I tend to call these the DAC color registers. Now the two main chips responsible for MCGA are these here. One of these is a video formatter gate array, and the other one is a video memory gate array. Now, the video formatter gate array is responsible for things like formatting the video output. For example, in low resolution modes, it has to double scan the lines. And the video memory gate array arbitrates between the various memory chips, of which there are 3, and of course the system character ROM, which is actually in the main BIOS chips over on the right hand side here. This is the back left of the machine, and that's where the video output is, by the way. Some viewers asked what kind of connector this is. Well, it's just an ordinary 15-pin VGA connector, and you can plug it into an ordinary VGA monitor. So basically we have two 32 kilobyte VRAM chips here for the video modes, so a total of 64 kilobytes of memory, and that's going to be important later on in the video. This chip here is an 8 kilobyte chip, and that is for text mode RAM for the various text modes that are available in CGA. So something that you should know about the MCGA is that it was basically based on CGA, not EGA. So CGA came out in 1981 and EGA in 1984, but instead of building on the latest standard, IBM did a fairly good CGA implementation here. A lot of the features and registers of the CGA CRTC are actually available in the MCGA implementation. And in fact, it doesn't offer EGA modes at all. So this is rather interesting. So what I want to do first is go through the modes that MCGA does offer, and that'll help us understand a little bit better about how the VGA adapter sort of builds on this MCGA. These are the CGA video modes, which I've divided into text and graphics modes. So modes 0 and 1 are basically the same thing on a CGA monitor. They're a 40 by 25 text mode, and similarly 2 and 3 give you an 80 by 25 text mode. The difference here is actually that on a composite monitor you get black and white and colour respectively. But we're not going to talk about composite today because MCGA and VGA don't have composite output, so it's not really relevant to today's story. So the graphics modes 4 and 5 are the gaudy CGA graphics modes that you would be familiar with from CGA games at 320 by 200 resolution. And these allow 3 colours plus 1 background colour. And the background is usually black but can be set to any of the 16 colours that CGA is capable of. Of course, you still end up with just 4 colours at a time unless you get into some hackery. Now, Mode 4 has 2 palettes and Mode 5 has 1 palette, and each of those has a low and high intensity mode. But as I said, each of those only gives you the 4 colours. Then there's Mode 6, which is a higher resolution graphics mode, 640 by 200, but it's only 2 colours. And this is basically all you get in graphics modes. The reason is that you only have 16 kilobytes of memory, so there's not very much more you could really do. Now, people would complain if I didn't mention the 160 by 100 mode, but this is really just an 80 by 25 text mode with the character height hacked, and with the characters set up so that you have half the character in the foreground colour and the other half in the background colour, and then you can just set those separately. So this effectively gives you a 160 by 100 low resolution mode, but with 16 colours, which a few games actually use. Now, I'm not going to mention the composite tricks. There's a whole load of hacks you can do with composite modes, and if you want to know about that, look at the 8088 MPH demo, which does incredible things with very large numbers of colours using NTSC artifacting. But that's not part of today's story. So MCGA offers all of the CGA video modes, but interestingly it doesn't offer the EGA video modes. So first of all, let's have a look at what MCGA adds in addition to CGA. There's really only the 2 extra modes. There's the mode 19 that we've been talking about. So this is similar to the 320 by 200 mode in CGA, but it offers 256 colours instead of 4 colours. And the other mode that's available is just a black and white mode, so a monochrome 640 by 480. So it's very high resolution, but not used in a lot of games because of the lack of colour. And that's really all that it offers you in addition to CGA, which is quite surprising. And you might notice that this is certainly going to use more memory than the CGA card. Here we had 16 kilobytes of memory, and there's 2 bits per pixel. Here we're going to need 8 bits per pixel, which means we need 4 times the memory. And indeed, MCGA has 64 kilobytes of video memory. What we're missing on MCGA are the EGA video modes, and there are some higher resolution graphics modes, or they have higher numbers of colours than CGA. And there are also text modes that are missing, for example 80 by 25, but it uses an 8 by 14 pixel character. And the 80 by 43 text mode, which means there's a lot more lines on the screen, uses the standard 8 by 8 pixel characters, but it gives you more text in the vertical direction. So none of that is available on MCGA. It seems that IBM were just keen to extend the capabilities of CGA, at least for the MCGA adapter. The other thing that EGA provides is the monochrome text mode of the monochrome display adapter. That's also not available on MCGA, by the way. But now we come to VGA, and you might be imagining that there's going to be a whole load of additional graphics modes here. But you're almost certainly thinking about Super VGA, at least officially by BIOS mode. The only thing that's really added is a 640/480 16 color mode. There are some text modes that are added. There's an 80 by 25 and a 40 by 25, now with a 9 by 16 pixel character cell. And you can even go up to an 80 by 50 text mode with the normal 8 by 8 pixel characters. But I'm sure that you're saying, I thought VGA was a 256 color adapter. Well, indeed it is, but it provides that using the mode 19 that we've already discussed, the MCGA mode. That is the 256 color VGA mode. But this only tells half the story. First of all, VGA provides the monochrome text mode, all of the CGA modes, all of the EGA modes, all of the MCGA modes, and then adds these on top. But in addition to that, the VGA adapter is really hackable and flexible, and so you can get a lot of other modes that are not bias modes just by hacking the registers. In particular, you can think of the VGA as being three underlying resolutions, if you like: a 640-400, a 640-480, and an 800 by 600 if your monitor goes up to that. And then everything else you can think of as being derived from that, either by reducing the number of horizontal pixels or vertical pixels, or by doubling everything. For example, a 320 by 200 could come from a 640-400. Just by doubling everything. So the Mode X that I'm going to talk about today is one of those hacked modes. Now the 320 by 200 256 color mode also has another alternative, sometimes referred to as Mode Y, which is the same resolution and colors but operates in a different way. So that's another famous hacked mode that's available on VGA. So in order to show off what these hacked modes are all about, I'm going to put up some games and do a comparison between what you can do on MCGA and what's different about the VGA. The first game that I want to show here is one we've already seen in the previous video. It's Revenge of Defender, and these are the video options that it offers. You'll notice that there's no specific MCGA mode here. It does support the MCGA mode, and I'm using my IBM Model 30 here. But it's just supported via VGA 256 color mode, as you might imagine. And what you'll notice is that it's a nice high color experience with 256 colors, but the big problem, as we saw last time, is that the scrolling is very bad. And Jim Leonard actually noted that the picture is being updated from the bottom to the top of the screen here, which is making it slower than it needs to be. But even so, I think on this particular 8086 machine, we wouldn't expect it to be much faster anyway. Now, I am as curious as you are what will happen if we run this game on a genuine VGA adapter. So I'm going to put it into my Compact 386S, which has a VGA implementation, and see how things differ. It'll still be the same monitor, my Compact 386 monitor, but it's going to have a genuine VGA. Well, this is the 386, and if you're anything like me, you can't actually tell whether this is running smoothly because of some VGA feature, or whether it's just because it's running on a 386, which is such a fast machine. So what I'm going to do is put this on a slower 286, still with a genuine VGA implementation, and see if we can spot any of that updating that we saw previously. Well, here it is running on my 286 at 12 MHz, and I'll select VGA just as we did before, and let's see if there's any difference in performance now. And I think you can see that there is a line still running up the screen every time it updates, so it looks to me like they have implemented this in the MCGA mode, even on a real VGA card, and not bothered to implement smooth scrolling. So they're just filling the screen in every frame with pixels in real time and not bothering to do any page flipping or anything like that. My guess about the reason for this is something to do with that foreground, which is scrolling past very, very fast compared to the background, which is scrolling slowly. But I haven't really sat down to think through why this would necessitate doing it in this particular way. At any rate, this is an example of a game that really uses the MCGA mode only, as far as I can see, and doesn't have a special implementation for smooth scrolling in VGA. Well, one game that does scroll smoothly, even on my 286 here at 12 MHz, is Pinball Dreams. Now this game is still running in 320-200 256 color mode, but on a VGA adapter, as you see here, it's actually using Mode Y. and it just has a different memory layout, which I'll talk about a little bit later, and it allows for this scrolling effect. So you can see that there's no updating like we saw in Revenge of the Defender. So this is a good example of use of VGA adapter to give effects that weren't available on MCGA. However, this game does actually run on MCGA, so I'm going to run it now on the IBM Model 30, and we'll see what the difference is in terms of scrolling on that machine. Well, unfortunately, this is all we're going to see when we run Pinball Dreams on the Model 30. On Moby Games it says it supports MCGA, but unfortunately it seems to require a 286. The other interesting difference is on the faster machine the copy protection is removed, but here on this machine it asks questions about words from the manual. Now that's not the issue here. I have the manual and it accepts the answers. It's just giving a black screen when you run the game. But at least we have examples now of games that run in genuine MCGA mode, Revenge of the Defender, and now one that, at least on a faster machine with a genuine VGA implementation, uses Mode Y. Same resolution and colours, but just gives smooth scrolling. So what exactly is the difference between these two? Well, it all depends on a feature that was found in EGA, but not CGA or MCGA, called planar graphics. You might remember that in order to set the color of a pixel in MCGA, all you have to do is find its offset in video memory and write the color value into the byte at that offset. But that's not how EGA works. Instead, there are 4 separate regions of video RAM called bit planes, one for red, one for green, one for blue, and one for intensity. And so in order to set the color of a pixel to, say, light green, I have to adjust the corresponding bits in the bit planes to not blue, green, not red, and intensity. Now this might seem more complicated, but there are actually some advantages to this approach. Firstly, if I change a byte in a bit plane, then I'm adjusting the color of up to 8 pixels at once, because each pixel corresponds to just a single bit in a bit plane. And secondly, the EGA card tends to make it easier for us by allowing us to specify which bit planes we're writing to at any given time. So we can select a color by choosing which bit planes we want to write to, and then just doing a single write will update all of those bit planes at once, potentially updating the color of up to 8 pixels at once. So this can actually be very, very fast for things like clearing the screen or drawing lines, so long as they're all of the same color, for example, or even scrolling, which I'll talk about a little bit later. But this is not how things work in the planar VGA modes. So let me describe that to you now, and we'll see how different it is to EGA. Mode Y is a 256 color planar graphics mode, and you can tell that 4 bit planes is not going to cut it here because that only gives you 16 colors like EGA. So in the planar graphics modes like Mode Y, you still have 4 planes in video RAM, but instead of interleaving color information between the planes, you now interleave pixels between the planes. So plane 0 would have pixels 0, 4, 8, 12 and so on. Plane 1 would have pixels 1, 5, 9, 13 and etc. And so this has the effect of interleaving the pixels between the planes. So in order to update a pixel in Mode Y, you first have to figure out which plane it's in, and then you tell the VGA card, okay, I want to set the active plane to, say, plane 2, and then in the processor address space there'll be a 64K memory window which will correspond to all of the offsets within that part of video RAM. So then you just figure out which offset your pixel is at in that plane, and after that it's similar to the MCGA mode. You just put the byte corresponding to the color value at that offset. So it's a kind of 4-for-1 deal in a sense. With a single 64K address window, you can access a total of 256 kilobytes of video memory by selecting one of 4 planes. Now you might wonder how the MCGA mode is implemented in a VGA card. And at least conceptually, it's exactly the same, except that there's a mathematical trick that's used to give the appearance of a linear layout of pixels. And that trick is called chaining. So the way it works, instead of the address in your 64K address space corresponding directly to the offset of one of the pixels in a plane, the address is broken into two parts. The lower two bits of the address are used to specify which plane you're accessing, and the rest of the address is used to specify the offset within the plane. Now this might sound complicated, but after a bit of mathematics you can check that it has the effect of making it seem like all the pixels are in linear order in memory. This will be address 0, this will be address 1, 2, 3, 4, 5, 6, 7, and so on. So this emulates precisely the way that MCGA worked in, say, the Model 30, in that your 64K address space now corresponds to each of the 320 by 200 pixels on the screen, all in linear order. Now there's a downside to all of this, of course, and that is you've now thrown away 2 bits of your 64K address space. You're using those to select a plane, and that means in total you can now only access 64 kilobytes of video memory. Now that's different in the other planar modes like Mode Y, where you had 64 kilobytes per graphics plane. So in those modes, in the other planar modes, the so-called unchained modes that don't use this chain 4 trick, those have a total of 256 kilobytes of memory, which means that you can do a bunch of tricks with them. One of the tricks you can do with more video memory is smooth scrolling. So the way that works is instead of starting plane 0 here, you tell the video card to start plane 0 here and adjust everything else accordingly. And you have to do a little bit of mathematics to check this, but the effect is that everything just moves to the left by 1 pixel. So just by changing one start address, I can actually do a shift of the entire screen. And if I repeat this process, I can actually scroll to the left very, very smoothly. Similarly, if I want to scroll up, I just have to move the start address from pixel 0 to pixel 320, and the whole screen will move up by a pixel. So I can do vertical scrolling smoothly as well. Now the other trick that I can do with more video RAM accessible is page flipping. And this is a standard technique for animation. The way it works is in the planar modes, like Mode Y, I have a total of 256 kilobytes of video RAM, but I only need 64 kilobytes for a 320 by 200 256 color graphic. So that means that I have enough space in video memory for a total of 4 pages. And so what I do is I draw my graphic in one of the pages that's not currently visible on the screen. And this hides the drawing process so you don't see it on the screen. And when I'm done drawing the graphic, then I do a page flip, which just means to set the active page to the one that I was just drawing. And that cleanly updates the screen instantaneously. And that means that I get a very, very smooth update between frames of my animation. So this gives very, very smooth animation, and so you can see that there are some definite advantages to having more graphics memory. So this is really the downfall of MCGA. Because only 64 kilobytes of graphics memory in total are accessible, you've only got room for 1 page. And you can't do scrolling because if you shift anything, you'll run off the end of video RAM. So this is why you can't do smooth scrolling on MCGA. In the original implementation, it's because there was only 64 kilobytes of memory. And in the VGA implementation, it's because they have to basically emulate that precisely. Now, it turns out that in practice, the way VGA cards implement the MCGA mode can vary from card to card. At least conceptually, what I've told you is the way that it works, but there are lots of tricks that can be done in hardware to do it a different way if they want to. And the funny thing is that you can actually do a write into video memory in one mode, switch the mode, and then read it out again in the other mode, and see exactly where in video memory it ended up putting the information. And so you will find some differences between video cards. But at least conceptually this is a great trick. You have advantages both ways. The simplicity of the MCGA or the extra smooth scrolling and animation of the Mode Y and other planar modes. Well, it's time we looked at a Mode X game, and the one that I picked here is Pinball Illusions. Some of the same people made Pinball Dreams that we saw earlier. Now, of course, this is running very slowly because it's a 1995 game, and I'm only running it on my compact 386S here, which is just really underpowered. Now, the main advantage of Mode X is that its pixels are 1:1 aspect ratio. So what that means is the pixels are perfectly square. And this means that if you're rotating objects on the screen, as it's happening here with these rotating cubes, then you don't need to do an aspect ratio adjustment as the object rotates, because everything is completely square. So that is the main advantage of this mode. The other thing is if you're drawing circles and things like that, they don't end up looking squished. So it just makes drawing graphics a lot easier. And people really weren't aware of this mode until it was popularized by Michael Abrash in a series of articles, which I'll talk about a little bit later. But basically, this is what the game looks like when it starts up. I'm going to now show the gameplay. It'll take a while to load, so I'm just going to pause the camera here and restart when it comes up. Well, this is what the game looks like when it's running, and you can see that it's scrolling very, very slowly here. Now, that's nothing to do with the video mode, that's just because the CPU is really too early for this particular game. Now, the scrolling is smooth scrolling, or it would be if it was running faster, and that's because this is a planar mode, just like the Mode Y that we talked about. It basically has the same memory layout with the planes, but it is a higher resolution mode with 320 by 240 instead. And as I said, the main advantage is the square pixels. But there's one other thing you might be noticing right now. There's no flicker in this mode, and that's because the 60 Hz that this uses is matching up with my camera. Basically, the VGA 640-480 resolution uses 60 Hz instead of 70. And because this is just doubled in each direction so that it gives you effectively 320 by 240, it is still underlying a 60 Hz mode. And so that's why you're not seeing flicker. You will see an occasional black bar running up the screen, but that is just because of a slight mismatch between the refresh rate of the monitor and my camera. You need very expensive gear to get around that. So anyway, that's all I really wanted to show you here. This is how Mode X actually looks and how it was actually used in games. The other thing that I wanted to do is give a little bit of information about where Mode X comes from. Now, of course, it was always there in the VGA hardware, but it wasn't described explicitly in the IBM reference for VGA. A lot of people had discovered it and it was used in games, but it was always a closely guarded secret, except for one man, Michael Abrash. Now, you might recognize that name since he's the author of a very famous book called The Zen of Assembly Language Programming. He also wrote a number of Dr. Dobbs Journal articles in the early 90s on graphics programming and related topics. And you might also know that he was one of the people who worked on the graphics subsystem of Quake. So he's a very famous guy, and if you go to the Mode X article on Wikipedia, it actually has a convenient link to the Wayback Machine, which has a complete archived copy of his book Graphics Programming Black Book, which is another very famous book by Michael Abrash. And it turns out that chapters 47 through 49 are all on Mode X. Now, he starts out by talking about the history of Mode X, which I just discussed, and then he goes and gives a list of the reasons why Mode X is so special. And he gives 5 different reasons. So the first is the square pixels, the 1:1 aspect ratio, and he gives the example that I did of drawing circles, which is much easier if the pixels are square. The second thing that he mentions is the page flipping, which we discussed for the fast animation. And the third thing is that you can actually use the planes to do very, very fast pixel processing. So it turns out that just like EGA, you could update all of the planes at once. You can do the same with VGA. And so this means that you can do very, very fast processing, depending on your application, of course. The fourth advantage that he gives is that it's quite simple. There's 1 byte per pixel and you just put the color value in. You don't have to go and set some registers to tell which bit planes to update in order to draw a pixel in a given color. So it's much faster than EGA in that sense. And the final advantage that he gives is something we didn't discuss, and that is that all the extra video memory that you have available, you can use it for storing small graphics. If you like, use it as off-screen memory. And there's a feature we didn't discuss called the VGA latches, which allow you to really quickly copy those images 4 pixels at a time onto the screen. So this makes for very, very fast VGA to VGA copying, which can be used to put images on the screen extremely quickly. So those are his 5 advantages of Mode X, and the 6th one that he gives here is a bit of a joke. He says it's a little bit hard to use. But he does go on to give examples of how to use it, including explicit assembly language, printouts that you can actually just copy in and use yourself. So it's a really fantastic article, and I recommend taking a look at that. It's freely available here on the archive.org. This is how Mode X became popularized, and once people started reading these articles, lots of people started using it, especially in demos, but also in some games. Anyway, that's all I wanted to talk about this week with Mode X. We're going to come back to this topic again, I'm sure, in the future, and we'll certainly have many other graphics-related topics and old hardware. So if you like this style of content, then don't forget to like the video and subscribe to the channel, and we'll see you in a later video. Bye.